All right, hello everyone, welcome back. We'll continue on the energy balance lecture. Where we left off was discussing types of energy. So there's a number of different types of energy, one being chemical, so that's the energy that's stored within the bonds of different molecules. For example, gasoline or petroleum would have a lot of energy because it has a lot of chemical bonds that can store that energy. There's kinetic energy, which we discussed before, which is the movement of atoms around. There's potential energy, which is the energy due to the position of an object, such as if you put an object high up on a shelf, it has more gravitational potential energy than something lower down. There's nuclear energy, which is the energy stored within the nucleus of an atom, the protons and neutrons. There's the electromagnetic energy, which is the light or different wavelengths of light and the energy that it contains. And then there's mechanical energy, such as energy in a spring or, for example, a leaping frog, the legs of the frog. So these different types of energies can transfer from one to the other. We can see that here, this race car going down the track, it starts off with a bunch of potential energy as it's high up, and that potential energy then transfers into kinetic energy as it moves down the slope and builds up speed. But it's important to realize that the total amount of energy in a system is constant throughout that time. And we can see that too here when we put friction in as well, is that the skier starts off with a lot of potential energy, and then as it moves down the slope, it gains kinetic energy, and then finally when it hits this unpacked snow, then it will lose that energy to friction, and that energy goes to heat. That was represented as W here in the snowpack, and it'll lose speed as that heat is generated due to friction. So there's a number of different ways that we can heat things or change a system. One of those is an adiabatic process. Adiabatic means that heat doesn't leave the system. And this is often the case for a lot of transfers of material within the Earth's atmosphere. We'll talk about that. Also, isobaric systems are also pretty common. So these are systems in which the pressure doesn't change, and this being an example of one where you have a hot pad heating a volume of gas, but that gas has a plunger on it that is allowed to move freely. And so as it heats up and the temperature increases, the volume is also allowed to increase so that the pressure doesn't change as a result. And these are two different types of changes to a system that will become a lot more relevant as we talk about different systems in the atmosphere. These two different types of systems are dictated by, it's called the ideal gas law. You might have seen this in a physics or science class. But all it really says is that the pressure and volume of a unit of gas is proportional to its temperature. So as you increase the temperature of a unit of gas, then also the pressure is going to increase as those gas molecules move more quickly and exert more pressure on their surroundings. The same is true for volume. So if you increase the temperature of a unit of gas but keep the pressure the same, then the volume also has to increase and it expands as that temperature occurs. One way this really comes into play for the atmosphere is a process called adiabatic cooling. And this is a process that forms a lot of clouds. And so oftentimes you'll have water vapor generated on the surface, as such as a lake that has evaporation occurring, and that water vapor rises in an adiabatic process. So as it rises, that heat is not lost, but the pressure is decreasing. So as you move higher up in the atmosphere, you have lower and lower pressures, and therefore the temperature has to decrease proportionally, just like in that ideal gas law. So as you go higher up in lower pressures, you decrease the temperature until finally it reaches the condensation level. That's the level in which it's no longer water vapor and it starts to form a cloud. And you have these negative temperatures where you have cloud formation occurring. And that's why a lot of times we see clouds that look like this, where you have water vapor coming up and then it reaches some limit where the temperature is decreased enough, so you have condensation occurring, and it forms these very flat bottomed clouds just like this, with more condensation occurring above that limit. So next we're going to be talking about solar energy. So a lot of times the heat that drives a lot of the processes on Earth is predominantly driven by solar energy, energy from the sun. And this is a really cool picture that was recently taken by a satellite, I think. And it shows a very zoomed in picture of the sun. And you can see different eddies and turbulent conditions that are going on right on the surface, with different hot spots and stuff like that. So as I said, the Earth's predominant energy source is the sun. And it's important to realize the sun is gigantic. It is 1.3 million times larger than the Earth. These are what the Earth would look like if you tried to fill the sun with little Earths. And so, because the sun is so large, it produces a lot of heat, and it has a very high temperature. And so, all that temperature causes radiation. Remember back to when we were talking about different types of heat, radiation being one of them. So if you have a hot object, it'll emit electromagnetic radiation. And the way that it does that, and the wavelengths it does that, is defined in a curve just like this one. And that curve is defined by what's called the Stefan-Boltzmann law. And all that law says is that the energy radiated from a substance is proportional to its temperature to the fourth power. So you need a very large change in temperature in order to change the amount of radiation that's being emitted from an object. And that radiation tends to have this kind of skewed bell curve shape. The yellow line would be the kind of idealized curve of the electromagnetic radiation, the light that's being emitted by the sun, with the intensity here on the y-axis and the wavelength on the x-axis. The sun, though, does reabsorb some of its own energy, and so this curve that it's actually experiencing is not quite ideal version, and it's actually closer to this orange version. And then the energy that actually reaches the Earth is this kind of black and rainbow, the rainbow indicating the light that's within our visible spectrum here. And so you'll see that there's a couple interesting features to this blackish curve here. One being that there's a number of dips, such as these ones in here. And those are caused by different molecules in our atmosphere, such as carbon dioxide or methane or water, that's absorbing a lot of that sunlight and reflecting it back, or converting it to heat so it doesn't hit the surface as electromagnetic radiation. And also another important thing is that the peak wavelength that that hits the Earth is right around the green wavelength, which is one of the reasons why plants tend to absorb a lot of green light, or they tend to absorb blue and red light because the green light is so intense. But you may be asking, if the sun is emitting mainly green light, why is the sky blue, and why does the sun kind of have a yellowish color to it when we look in its direction? And the best way to answer that is with this video here.
The sky is not blue. It's mostly transparent air, which is, at best, the color of whatever light it scatters. Sure, it does scatter blue light more than red light. In fact, the higher the frequency of light, the more it gets scattered by the atmosphere. So ultraviolet scatters more than blue, which scatters more than green, more than yellow, more than red, more than infrared. But still, only a tiny bit of light scatters, while most of it goes straight through, which is, how the sun can light up the ground, why we can see the moon and stars through the atmosphere, etc. The sun itself actually emits a wide range of frequencies of light, and our human eyes perceive this particular combination as white or neutral in color. The vast majority of the sky appears bluish because sunlight that was trying to go somewhere else got scattered by the air and instead ended up in your eye. Bummer. It still has a wide range of frequencies in it, with slightly more blue than in white light, roughly the same amount of green, and less red. You can see a simple demonstration of this on a computer if I take a white background, add a bit of deep blue, and subtract a tiny bit of pure red. I get a nice sky color. And the reverse effect happens when you look near the sun. Light that was trying to get to your eyes gets scattered away, so the remaining light has a lot less blue and slightly more red, compared with white light, which is why the sun and sky directly around it appear yellowish during the day. At sunset, there's even more air for the light to scatter off of before it reaches you, hence the even richer oranges and reds. And of course you can do the computer demo again, this time subtracting pure blue and adding a little red. Voila! Noontime sun. Subtract more blue and add even more red? Sunset orange. So the sky is not blue. It's a stage upon which all colors dance. Red colors tend to dance in straighter lines, green colors more randomly, and deep blue colors dance the most frenetically of all. Yet at some point, they all ultimately dance their way into your eyes, and my eyes, and to the earth and into space, so that everyone everywhere can appreciate the grand ballet of light.
Great. And so we'll take a break there, and we'll continue for the last and final part of this lecture.